All right, we are at the top of the hour, so let's go ahead and get started. Hello, everybody. Thank you for joining today's webinar on low power speaker verification for edge devices. My name is Amanda DeFelice, and I'll be kicking things off and introducing our speakers for the day. Before I introduce our speakers, just a friendly housekeeping item. You should see a Q&A section at the bottom of your screen. If you have questions as our presenters go through the materials, please drop any questions in the Q&A section. We'll do our best to answer those live as we go through this, but we've also got some time reserved at the end to have some open Q&A and discussion. So with that, I'll introduce our speakers. First up, we have Andy Hagen. Andy is the Director of Machine Learning at Sensory, where he spearheads R&D projects to develop innovative speech and sound recognition solutions. Andy has a PhD in computer science from the University of Colorado at Boulder and has over 2 decades in the field. Andy has worked and studied in Germany and the US and brings a global perspective to his work. Next up, we have Jeff Rogers. Jeff is the VP of Sales and Marketing at Sensory. Jeff has been influential in the development and design of hundreds of products over the last 29 years that use Sensory's technologies. He has licensed speech recognition, voice biometrics, and computer vision technologies to companies like Apple, Amazon, Fujitsu, Garmin, GoPro, Google, Honda, Microsoft, Samsung, Zoom, and many others. And finally, we have Christian Coughton. Christian is a research scientist at Sensory, where he specializes in the research and development of biometric face and speaker verification technology. Christian holds a PhD in software engineering from Auburn University and brings over 10 years of experience building software to the team. Christian's roots in computer vision allow for an interesting and fresh perspective into his current interest in speech and natural language processing. Jeff, Christian, Andy, thank you all for joining us today. And with that, I will kick things over to Jeff.
Thanks, Amanda, and thanks all for joining. This is a really timely webinar for us because lately we've gotten a lot more interest in our speaker verification. Back when we first started Sensory back in '94, I think it was the very next year, '95 or maybe it was '96. We actually developed a voice password chip, and we saw the interest in voice biometrics way back in '95 and '96, and it was a really interesting chip, and it was really designed around, hey, I just want to add a voice password to products. And so we've been doing biometrics for a lot of years, obviously, but more recently we've seen a huge growth and interest in voice biometrics, as well as our face biometric and computer vision. And I think a lot of this is that more and more devices are connected now, and there's a real need for ensuring that it's me using my device. So whether this is adding and combining voice biometrics with wake words, or with our speech to text or user-defined wake words, or just straight voice passwords, we're seeing a big growth there. And I think with LLMs and as exciting as they are, and the new opportunities and things that are being opened up with LLMs, there's going to be a need for a local biometric that's running on your own personal device that says, okay, yeah, this is Jeff, and this is me asking for these types of things, rather than having others be able to hack in and do things that you might not want them to do. So, and we're seeing this interest across all the industries that we work in. So why Sensory? We've licensed over 200 companies. All the logos you see on the right side there are real customers that have done real products with Sensory. So we're not new to this game. We've been doing this for a while. We've shipped over, or our technologies have been shipped in more than 3 billion products worldwide. So it's a really nice stat, and it's obviously fun to say, and it's after a lot of work and with great technologies and tools that allow us to go across so many different industries. Our market focus today is automotive and medical and CE, and we're definitely seeing a need and usage already across these industries for voice biometrics. And so today we're going to really talk more about our voice technology and the different offerings that we have there. So why is on-device technology important? First off, we have a full suite of face and vision, voice and vision technologies. So we're definitely known for wake word and wake words, running multiple wake words at the same time, full speech to text, sound ID, Last month we did a sound ID or an EVD webinar that was really well attended and pretty interesting. And the next part of that is the voice biometrics that we're doing. So why is why on device is important? Well, it needs to be always on, always available. I can't have to rely on a network connection or internet or any other thing. We're working with companies right now that are already designed us into things like laptops such as NEC mobile phones and tablets. We're talking with companies that are developing door cameras and other things where you can't rely on a Wi-Fi connection and a network connection. And so again, running completely on device is really important. Complete data privacy and control, that's also important. So when I enroll my voice password, it stays on device. It's my voice and my password, or if I'm using our computer vision, those images or templates are not going anywhere. They stay completely on device. We have a lot of flexibility in the platforms that we run on today. We can run deeply embedded. So our TrulyHandsfree has a version of speaker verification that runs with it as well. And so that can run down on DSPs like hi-fi based DSPs or ARM based cores such as M0s and M4s and M7s. And then of course we can also run on CPUs and GPUs and others, NPUs as well. So a lot of flexibility there. As far as cost of ownership, it's super low because I don't have to worry about cloud connectivity. Every time you go to the cloud, there's a cost to doing that. And the more users you have and the more products you have, those costs can grow very quickly. With Sensory, it's very easy to define because it all runs on device. And again, really market proven with the experience that we have today. So let's jump into more of the technical discussion, and I'll turn things over to Andy and let him talk through his slides here.
All right, thanks, Jeff. Yeah, so I'm going to be talking a little bit about our TSSV SDK, Truly Secure Sound and Voice SDK. And the speaker verification part later on is a part of this SDK. So here we have four broad technical domains. We have wake words, sound ID, speech to text, and voice biometrics. And so for wake words, I'm going to go through them briefly and then a little bit more in detail afterwards. Wake words are just phrases, terms. You continuously listen to some audio and then it triggers with a specific term. Sound ID, we have a broad offering of 16 different sound classes, and we also have an automotive solution for sirens. Speech to text, that's actually brand new. We have a highly accurate speech recognition system just added to this SDK. Can be general or tailored towards a specific domain. And last but not least today, voice biometrics. There we have text-independent speaker verification, text-dependent speaker verification, and also enrolled wake words. The TSSV SDK runs on many platforms. You can see Android, iOS, Mac, Windows, Linux, and we also support a bunch of programming languages. C++ comes natural because the SDK is implemented in C++. And then we've got wrappers for Python, Java, Swift, C#, and Objective-C. And the SDK, when you get it, comes with sample code and tools. Yeah, next slide, please. So let's jump a little bit into the wake word verification. So what is that? You probably know it, or you can imagine what it is. You continuously listen to an audio stream of mostly speech, probably. And then whenever there's a custom or predefined phrase that you want to hear, for example, hey Sensory or Voice Genie, then it triggers something. It can trigger something on your smartphone or start a voice assistant and so on. What we can also do is link your voice to a voice profile, and that happens in the background. So you have a seamless enrollment mechanism. You say the wake word, and the system also knows who it is after a few tries and examples. And then in general, like what the audio filtering does, so how you can apply the system is you let this wake word detector run, And whenever the passphrase comes, um, it it listens to to what comes right after. So, hey sensory, take me to, for example, in the automotive field, and that take me to is then routed to an outside service, maybe to the cloud, maybe it stays on device. You can, it's pretty flexible, but it happens. It's very well integrated, so that the wake word comes, and then right afterwards you can say whatever you want, and this is processed. And yeah, that's mostly the wake word. Then on the next slide, we go into the sound ID part of TSSV. I talked about that one in the last webinar with emergency vehicle detections. And here I'm going to talk a little bit more also about the broader offering of sound ID. And we have 16 different sound classes in general. 3 domains: health, safety, and home. And you can see the health domain consists of things like coughing, sneeze, snore. Safety is glass break, gunshot, shouting, whatever could occur in such a setting, fire alarms, and sirens, of course. And then the home domain is whatever could happen in your home or household: alarm clock, baby crying, dog barking, cat meowing, and so on. Then we have the siren detection. We have that again, but now optimized for the automotive sector. That means it's optimized for specific voice, not voice, but sound backgrounds, like street noise, in-vehicle car noise, and so on. So it's very robust against false alarms in those settings. And it triggers whenever there's an emergency vehicle: police cars, fire trucks, ambulance, and so on. What the Sound ID offering also has is a sound scene tracking. This is, you can imagine when you, for example, run music in the background, or you have speech, female speech, male speech. This is like a probability value over time that gives you the probability or the current estimate of, for example, music being played in the background. So it's not like an event, but it's more like an ongoing probability value. And last but not least, we can always, if you don't see your desired class in this list, we can also can always extend that. We just need data, a little bit of training time, and then we're pretty flexible with this one. On the next slide, I'll talk about our latest, not latest, almost latest edition. The latest one is what Christian would be talking about. But we also have a speech recognition solution, a speech-to-text solution now, which is highly accurate, fast, low latency, and real-time performance. We have batch mode, streaming mode, and we have small acoustic models of down to 5 megabyte only, and it goes to about 140 megabyte. We currently support 36 different languages. Our language models can either be domain specific or just general purpose, and we can tailor them towards a specific new domain. One very interesting thing is the custom vocabulary support. So imagine that you have a list of names or specific terms that you're interested in, and you want to have those come out of your engine exactly how you want them, correct spelling and everything. You can add that list basically on the fly, and it will be recognized accordingly and not have a different kind of spelling, even though it might sound the same. And then we have domain adaptation, so we can adapt our system to different noise levels or use cases tailored to domains. As I said, we're pretty flexible there. We just need to know you need, and then we can do that. And then the most important topic today is voice biometrics. We recently added TISV and TDSV, text-independent speaker verification and text-dependent speaker verification. Imagine this is, you can say any spoken word versus a passphrase to be accepted. That's the difference. And then we also have a kind of a liveness detection. You basically get displayed it's a sequence of digits, and then you need to say those digits. This prevents from an attacker, for example, playing a pre-recorded sample of somebody's voice. You need to say exactly that sequence that's displayed, and therefore you have this liveness check. Then, of course, we can adjust the sensitivity here to different security thresholds. And you might want to have an application that can run a little bit looser or some that has high security. And last but not least, we can work under different environments, noise environments, and we're language independent. That gives a lot of flexibility. And
Hey,
with this,
hey, sorry, Andy, just a couple of questions that have come in while you were talking.
sure.
And you touched on it a little bit, but one of the questions is, how does the biometrics block someone using AI to mimic my voice? And you mentioned briefly that one of the approaches that we have for that is that we use an active liveness check, and we can do that through, for example, and I'll show a demo of this later in the webinar where we use digits, and I'll enroll saying the digits, and then as I need to authenticate myself, I'll be shown six digits that are randomly generated, and they change every single time. And so it has to be my voice speaking those digits. And so I think those are the types of things that we're doing right now to block somebody having a recording of my voice. I do have several people that have asked me, how do you handle, AI generated that sounds just like me, and could you generate that quickly and speak those digits? I don't think there's any biometric that's 100% secure, but what we try and do is make it really, really hard, obviously, for somebody to be able to spoof in there. And so again, these are some of the things that we're doing right now. Another two questions came in, basically asking the same thing. What's the power consumption if we're always on listening for a voice biometric? And the way that we can do that is if it's combined with our wakeword technology, which a lot of times it is, our wakeword technology can run very low power at the DSP level where we're pulling 4 MIPS or less. And so it can be ultra low power. In fact, a few years ago, we worked with Samsung TV, and they had a remote control that had 2 AAA batteries. And the rule was that they had to be always on, always listening, and they had to last for at least 6 months. And we totally were able to accomplish that. And so what we can do in a voice biometrics solution is that we can run our TrulyHandsfree wakeword that also has speaker verification. That can run very, very low power. And then when the wakeword is recognized, then it can send the audio to the TSSV algorithm where it can say, okay, yeah, now let me confirm that this is the right person. And so it's kind of a 2-step process. And so that's how we can run very low power. Okay,
Yes.
back to you.
Thank you. That was basically my part. And now Christian will tell us more about the specific voice biometrics today.
Awesome. Thank you very much, Andy. Before we dig into the specifics of speaker verification, I'd like to provide some high-level definitions just so that we have a strong foundation for the remainder of the talk. So speaker verification, that we also refer to as voice biometrics, is really any technology that provides a mapping between human vocal samples and some sort of identifying code that allows us to distinguish which particular person is speaking among a set of individuals. In practice, it's a really vital component for any sort of voice-based interfaces. This could be personal assistants like Alexas, Google Homes, things of that nature, autonomous vehicles, and then likewise the most common use case of unlocking a cell phone or a personal device. As Andy mentioned, it can be either text independent, where matches occur regardless of the speech content. What you say doesn't matter. It's really just a question of who you are. Or it can be text dependent, where we also look at the actual speech content of the signal and only trigger when the particular phrase that was enrolled is uttered by the same person whom enrolled it. Now, within our TSSV SDK, we have architected speaker verification in a 2-stage design. What this allows us to do is provide a very lightweight preliminary stage that filters out a fair amount of the input audio signals. For continuous listening types of applications, this helps reduce the overhead needed to perform inference with the models. Outputs of this first statistical first stage are then fed to a much beefier DeepNet revalidation solution, which helps us to reduce FAs and improve security for a very negligible increase in compute cost. Now, speaker verification in terms of the user experience is really broken down into 2 independent flows. The first of which is the enrollment stage. This is where speakers first interact with the system to provide input data to build an enrollment. For text independent mode, this might be T seconds of audio being collected where the speaker is reading back any sort of phrase that they want. The speech content doesn't really matter, so we just measure the amount of time that they speak, typically around 12 to 15 seconds per enrollment. For a text-dependent mode, it's not necessarily a measure of time, but instead a measure of the number of times they utter a particular phrase. So we'll have a speaker say their passphrase maybe 3 or 4 times, and then treat that then as the enrollment of their voice. As enrollments are learned dynamically, they naturally have to be stored and thus require a little bit of disk space or somewhere to put them. Ours tend to be about 50 to 50 kilobytes of data per speaker enrollment. And the way that we have architected TSSV allows individual users to enroll up to N different users for recognition. So it's really well catered towards small home environments, office environments, anywhere where you not only want to determine whether or not a speaker is speaking, but distinguish among a group of speakers. Once you've created an enrollment for either one or more speakers, audio streams can be continuously analyzed and then matches can be produced at the verification stage. The way that we measure the quality of a speaker verification solution really comes down to 3 key metrics. The first of which is the false reject rate. This is the rate at which true speakers are denied from accessing their personal device. So you might think of this as, you enroll in a device, you come back later and you speak to it, but it doesn't let you in. That would be a false reject. On the flip side, there's the imposter accept rate, which is the rate at which adversaries are able to break into your phone. So imagine you make an enrollment and you give it to a family member or a friend, and they're able to somehow access your device. That would be considered an imposter accept. And then lastly, since we operate typically in a continuous listening environment, there's this notion of a false accept rate, which is the rate at which your device fires just on sort of arbitrary acoustic information. Anybody that has a personal assistant like an Alexa or something might be familiar with it firing when you're listening to a podcast or watching television. You see the rings light up and it's not really clear why. That would be considered a false accept in this case.
Hey Christian, one question that just popped in is what's the max number of N different users for TSSV?
That's a great question, actually. So we typically target a relatively small N. I think it's most optimal at the tens to hundreds range. Naturally, the larger N grows, the more overhead there is from comparing against all of these enrollments. I don't believe we have a hard limit within the SDK, but typically performance is best with smaller sets of N. The more people you enroll in these hyperspace types of models, the more holes you're sort of effectively poking in that space. All right, within the SDK, security can be calibrated really to fit any type of use case. Within TSSV, we offer 10 different calibration points where we control the imposter accept rate and then measure the false reject rate or false accept rate associated with that imposter accept. This allows end users to cater the system really towards the security level that they need. For a high security application like maybe banking information, you might want a significantly lower imposter accept rate than, say, for a personal assistant that operates in a home and may not necessarily provide access to as much secure information. In order to produce this, we simulate the enrollment and verification procedures based on a large amount of speaker data. We hold out a little bit of data for each true speaker, and that allows us to measure the false reject rate by comparing directly the true speaker against their enrollments. And then likewise, those held out speakers can be compared against other speakers' enrollments to measure our imposter accept rate then. Now, in this day and age, open source and academic models are quite easy to get. There's a lot of them out there that are really well designed and performant. The problem tends to be that these models are exceedingly large, the parameter counts are very high, and thus the inference latency on CPUs, embedded devices, and edge devices tends to be at a point where you can't really use these models there. So what I've shown here is we have 3 models from the academic space, and you can see the parameter counts are in the tens of millions and the model sizes tend to be in the double-digit megabyte range. And then inference latencies are relatively high at 38 to 50 milliseconds per inference. Even on the smaller side with the model here, that's about 1 million parameters. its sort of complicated architecture lends itself to poor inference latency, and we see actually the highest inference latency from this very small model. At Sensory, we have found sort of the sweet spot of size and accuracy and have driven the sizes down to as low as about 0.6 million parameters, 700 kilobytes for that model, and all of our inference latencies are within the real-time range, all the way from 6 milliseconds per inference call all the way up to about 16 milliseconds, which is 60 frames per second. Now, accuracy obviously is a very important component when it comes to building any biometric technology. If the accuracy isn't sufficiently low, then the system either produces too many imposter accepts and isn't secure, or too many false rejects and makes for a really poor user experience. As I mentioned, our system is based on a two-stage design. What this allows us to do is improve the imposter accept rate significantly as compared to simply using just one stage. What I've shown here is two different plots. On the left, you'll see the false reject rate plotted in terms of the security threshold. So on the x-axis, we have our 10 operational points, and on the y-axis, we have the false reject rate measured in terms of percent. And as you can see, for all but the very high security thresholds, the addition of our second stage, as indicated by the green line, is relatively negligible compared to simply the first stage indicated by the blue line. On the right side of the slide, you can see imposter accept rate reported in a very similar way, with security along the x-axis and then a percentage along the y-axis. And then the first stage shown in blue and the first and second stage shown in green. And you can see a significant reduction in imposter accept rate due to the addition of the second stage. In other terms, you could say that this is a significant increase in your security by adding the second stage revalidation model.
Hey, Christian, a question came in from the audience. Pretty interesting question is how does this how's the system perform in looking at these at the TISV accuracy model, and I guess text dependent, the same question. How does it perform if the user has a cold, or the user gets frustrated, or they get impatient, kind of thing? How do we handle that?
Indeed. So that's really handled on the data side. Our data contains many samples of different users saying, for the text-dependent case, saying the same phrase, or the text-independent case, many samples of different speakers with different channels, so different microphones, and with different prosodies. So the way that they're speaking is changing. So really, it's a data solution there. By collecting enough data, we can ensure that our model is robust to these variations in speaker presentation and style. Likewise, the same is true for background noise. So we train the model not only with samples of speakers, but samples of noise environments mixed in, which allows us to ensure that our system is robust not only to clean conditions like I'm in right now, but noisy conditions like train stations, airports, automotive use cases, and such.
Another question on TISV while we're on this slide is what CPU architectures were optimized for our TISV?
That's also a great question. So all of the metrics that we report for latencies are gathered from a Raspberry Pi 3. A little bit later in the presentation, we'll look at not only the inference latency, but the memory overhead from deploying the system on a practical embedded device such as a Raspberry Pi. All right, so to this point, I've primarily focused on discussing our text-independent mode, but I'd like to talk a little bit about our text-dependent mode. In practice, our text-dependent solution is modeled very similarly to TISV, where phrases are represented using one-dimensional embedding vectors. This allows us to perform similarity comparisons with very low overhead as compared to more heavyweight solutions like speech-to-text, which you can commonly find for wake words and text-dependent type applications. For the text-dependent mode, the revalidation models approximately double in size due to the addition of this sort of different modality and task. But the flip side is that the biometric accuracy actually improves, not only in terms of the metrics, but in practice, text-dependent models are significantly more difficult to break into than TISV models due to the reduced linguistic variability that we're typically operating with. So if you had an adversary that's trying to break into your system, maybe they've got some sort of AI that can synthesize your voice based on text. They'd not only need to know, well, A, what you sounded like, but B, what your passphrase is. And because our system never represents the passphrase as clear text, it's almost impossible for an adversary to know that passphrase unless they've somehow listened in on you and observed you uttering your passphrase. So it makes it, in practice, a lot more difficult to break into.
Hey, another question that just came. These are great questions, by the way. I appreciate everyone asking these questions. Another question that came in is, what security considerations are taken to protect the voice sample information, i.e. the 50K of data that's stored on device for authentication?
Indeed. So the security in terms of the biometric samples that we keep, the embedding representations, is really flexible and left up to the end user. So if there's an encryption protocol that your company is using, it's very easy to encrypt that data and store it that way. Likewise, it can be put into databases. There's always, with any sort of data storage, the risk of leak, but with encryption procedures, it can be reduced significantly. All right, so that's sort of the high level of the biometrics technology. I'm going to take a little bit of time to speak about the actual TSSV SDK as it relates to voice biometrics. And there's really 5 key enablers that make TSSV a great solution for voice biometrics. To this point, as I mentioned, it's a very small and lightweight solution, which makes it quite efficient. But at the same time, we're not compromising on accuracy to produce this small model. Likewise, the lightweight nature means that we have low latency, which ensures that the user experience from interacting with our system is seamless and fast. If your system is slow and doesn't respond very quickly, it's very easy for a user to doubt the security of it or just move on to some other alternative mechanism or forego security altogether. As was brought up by the question, our system performs well in noisy environments, and not only in noisy environments, but at various depths of field for various speaker prosodies or emotional stylistic representations of speech. The SDK enables us to deploy onto a variety of hardware platforms, anywhere from cloud deployments all the way down to very lightweight embedded devices like Raspberry Pis, Android phones, iOS phones, etc. And then importantly, our system is vigorously tested to ensure that it meets real-world performance expectations. We work a lot with our customers to ensure that what we deliver them is what they're asking for and not, something that we think is great and then ultimately doesn't work for their use case. Our system is tested to ensure that that does not happen. In terms of the detection characteristics of our system, it outputs 3 different signals that you can interact with in practice. So you get the similarity score against target enrollments that can tell you how similar 2 voices are. This is useful for applications that go beyond voice biometrics, such as like speaker similarity or document retrieval. Likewise, we provide the Boolean authentication signal. This is useful, for phone unlock, anywhere where you really just care about the yes, no for one speaker. And then finally, because we generalize to n sets of speakers or n speakers within a set, we provide the user label on verification, which tells you which user is speaking, so you can adapt your application code to provide catered functionality for particular users within that enrollment system. An important element of our system that is optional but quite powerful is the notion of adaptive enrollment. And as the name would suggest, this allows enrollments to be sort of learned online in a way that allows the system to change the enrollment based on changes in the speaker's prosody or stylistic representation. So queries that are verified within a certain threshold level can be integrated back into the enrollment slowly over time. This way, as speakers change throughout time, the system continues to be able to identify them securely. And importantly, the way we have designed adaptive enrollment really reduces the risk of imposters sort of slowly poisoning the system and ensures that that really doesn't happen in practice. All right, as I mentioned, our SDK is quite low latency. Not only are our models lightweight and quite quick, but the SDK itself, which bundles everything together, is quite fast. The response time is under 60 milliseconds for the end-to-end system, which is quite below the perceivable delay for most humans. And this fast response time ensures that users interacting with the system have a really smooth experience and really get into the secure elements of their applications quickly without any interference. Our system is not only optimized for latency, but footprint as well. So the RAM overhead that you encumber from deploying the solution is quite low. The SDK maintains a sliding acoustic history for text independent mode of 1.5 seconds. And then for text-dependent mode, about 3 seconds, which allows for slightly longer passphrases than you might see with a 1.5-second window. Despite the buffer lengths, partial speaker utterances can trigger biometric events. So as little as about 600 milliseconds of speech data in many cases can result in a successful authentication for either TISV or TDSV, depending on the length of the phrase that the user has chosen to enroll. Here I'll provide just a little bit of data for engineers in the crowd. Our first stage alone runs quite quickly. I've shown here not only the enrollment side, but the authentication side. The RAM overhead for the first stage and the first and second stage, both of which are shown just in the single-digit megabyte range. And the millions of instructions per second, or MIPS, is shown as well. The addition of the second stage for enrollment does encumber a little bit of additional overhead in terms of MIPS from processing all of the additional information. But enrollment really only accounts for about 0.01% of the actual use of the system. The primary use really comes down to authentication time. And with authentication time, we see that the addition of the second stage just under doubles the number of MIPS and likewise just under doubles the memory overhead as compared to the first stage alone. And this doubling of memory and MIPS is best seen relative to the increase in false accepts, which we see about a 5x improvement in false accept rate from the addition of the second stage. So for a little over double the compute complexity, you're getting something that's about 5 times to 10 times more accurate. And with that, I'll hand it back to Jeff, who will give you some demos of the technology and show you how it works in the real world.
Great. Thanks, Christian. Hey, there's a couple other comments or questions that came in regards to spoofing and how can we handle AI attacks and other. And earlier, as I introduced Sensory and our technologies, I did mention that we have both voice biometrics and face biometrics. And one of the ways that we can certainly fight against those attacks and the AI attacks is combining those two technologies. So if I've got a device and it's listening for a voice password and it has a camera, it can also look at me and say, okay, yeah, that's Jeff, and that's Jeff saying his voice password. So combining those things together can also help with that. So what I want to do is I want to show just a couple of quick demos of our biometrics here. So I'm going to screen share, and this is all running on an Android tablet, and as I mentioned, completely on device. So let me just share my screen here. And so I think you should be able to see that screen. So first off, if I go into the enrollment settings, you can see that there's different types of enrollment. There's text dependent, there's text independent, and then there's fixed phrase. So text dependent is where I enroll a specific voice password. It's language independent. I can say anything I want to say as long as I say the same thing again. You can see the enrollment here. The default is 4 times. And so I'll just use that one. Text independent is where I'm just talking and it hears my voice and says that's me talking. And then fixed phrase, a great example of this is when you buy a new iPhone and the first thing you have to do is say, hey, Siri 6 times. That's an enrolled fixed phrase. So it's learning your voice saying, hey, Siri. And with us, again, the enrollment is 4 times instead of 6. So let me start with text dependent first. And I'll just do a quick enrollment. I can say anything I want to say here. Voice password. Voice password. Voice password. Voice password. And so now I'm enrolled, and so I can change this to Jeff. And this is also going to use our wakeword technology as well. So as soon as I click authenticate, you can see up here this green line is bouncing and it's listening to everything I'm saying. And when I say voice password, then it's going to say, yeah, that was Jeff. And it's really small. You probably can't read that, but it also said model adapted because one of the settings I used here is continuous adaptation. And this is all running on device. Again, I don't have to go to the cloud for any of this adaptation. The enrollment was on device, the authentication's on device, and the continuous adaptation is also running on device. So I say voice password, and it's going to say, yeah, I got it. Someone asked earlier, how does it handle a cold as an example? So if I have a bad cold and my nose is stuff like this, voice password. it was still able to recognize me. Now you notice that it didn't say model adapted because it probably came in with a lower score. And so it said, well, that is Jeff, even with that really bad cold, but I'm not going to adapt that model. And so again, the adaptation algorithm is written such that if enough, I guess, check marks are in line, then it says, okay, I'm going to add that to the adaptation. And so over time, it continues to get better and better. Voice password. Okay, so let me stop that one. And let me switch to text independent verification. So text independent verification, the enrollment is very different. Instead of just saying the same thing 4 times, it's just going to learn my voice. And so here you can see that I can select the duration. The default is 12 seconds. I'll leave it at that. We could go down to 8 seconds. We could go as much as 20 seconds. The longer that I enroll, the better the template's going to be. And with both text dependent and text independent, it's really important that we enroll in a quiet background. What you don't want is to enroll with somebody talking next to you, because whatever the microphone hears, it's going to enroll that as your template. You wouldn't want to enroll with a motor running next to you, because that motor would be part of that, and so it would lower the accuracy. So important to enroll in a quiet environment, but then I can use in other environments. These demos, I use these at CES where it's extremely noisy, and that's okay because I enrolled in my hotel room, the night before as an example. So text independent. I've got revalidation turned on as well. And then later I'll turn on the liveness challenge to show you how that works. But let me start with this here first. So now I can read this little paragraph up here, but basically I just have to talk for 12 seconds. And down here at the bottom, you see this little progress indicator going along here. And it's basically just saying, okay, has it learned enough about my voice, how my voice sounds, the frequencies, and the other information that it uses to create that template. So now it's done. And as a sales guy, I have no problem talking for 12 seconds. That's easy. But to a user, you probably would have something that they would read. Some people have asked, can we do that in different sections so it's not all 12 seconds at one time? Sure, we could ask different questions. For example, tell me your name and tell me your address, and each one of those could be a kind of an onboarding kind of thing. Or we're also taking voice templates. So as soon as I hit authenticate, this is on and listening. And again, you can see the model adapted there. And up here at the top, you can also see recognition scores. So, and I give this demo all the time. This is an Android APK. And so if other people start talking, then it stops responding to their voice and only responds to my voice. In this demo, I've enrolled up to, I think, 6 people. I think it can do more than that. And so again, the earlier question is, how many people could you enroll to? And because I selected adaptation, you can see that it continues to adapt to my voice as well. So if I let that clear and I just start talking, you can see that the authentication happened within like 1.5 seconds. It's really, really fast. And then again, this could be combined with our speech to text such that, and with our text dependent, and I'll turn this off so it stops popping at me here, where the wake word could be text dependent. So I say the wake word and it says, yeah, I heard the wake word and that was Jeff speaking. And then maybe I'm talking to my TV, or maybe I'm talking to my panel in my house, or maybe I'm talking to my car. And the next thing that I say, set the temperature to 68 degrees. You can also say, okay, that was also Jeff speaking. And so in a car situation, maybe the kids, they don't get to change the temperature setting, but they can change their screen settings as an example. So we can recognize them. We can recognize using our speech to text. But we can say, yeah, that they're not the right user for this type of activity. So let me go back in here and let me turn on liveness challenge. And here I'm just going to use digits. And I think what I have to do is let me delete this user here and just make sure I've got the same settings here. Okay, so yeah, so I'm going to enroll speaking digits, and then it will randomize those digits to help fight against somebody that has a recording of my voice as an example. 069553, 923693, 190966, 867725. And so now I've enrolled my voice saying those digits. And now this is going to use, it'll use our recognition engine to recognize and make sure I'm saying the right sequence of digits that are shown. and it's using our biometric to make sure that it's actually me speaking. So now when I want to authenticate, 850598. No problem. And you notice that I even said O instead of 0. I might have enrolled saying 0. The recognizer understands the difference between those. And then you can see a really nice score. Scores, I think, go from 1 to, I don't know, 30 something. Maybe they go higher than that, but this is a nice high score. Okay, but what happens if I say the wrong sequence of digits? 093122. And basically says, yeah, that yes, it was my voice speaking, but I said the wrong sequence, and I'm still saying the wrong sequence, so it keeps rejecting, and then it timed out. All of this can be defined in software. So if you want it more secure, you give the user just a couple of seconds to say the digits, and don't let them keep trying. If you want more flexibility, well, then you can have that window out there longer, so give the person time to try again. 205545. So I just rifled through those, and yep, that's Jeff. And so again, if somebody had a recording of my voice saying 20 whatever I just said, well, the next time it's going to change again. So this is text independent and text dependent. Within this demo, and this is an APK, you can basically pick which one you want. I won't do the fixed phrase. It's basically like an iPhone where you say the same thing over and over 4 times. Under authentication settings, Christian showed earlier that there was a bunch of high settings and a bunch of low settings. And so all of this is adjustable within the SDK. So within the SDK, you'll have access to all those different settings. And you can basically allow the user to choose. Is it, do I want high security, which will have a higher false reject rate? Or do I want it more, is it more about speaker identification rather than verification? Okay, I'll use a lower security. I just want to see when I walk up to the panel, my panel in my house that controls the security system or, temperature and heat, and other things in the house. I just walk up, there's a presence detect. It says, oh, yep, there's somebody in front of me. It looks at me and says, that's Jeff, using our face biometric. Or I just say my voice password, and it says, yep, that was Jeff saying the wakeword as an example. So again, all those settings are adjustable within the SDK. And that's it for my demos. I'll stop sharing and turn things back over to Amanda.
Thanks, Jeff. Those were great. So we do have a couple of other questions coming in the Q&A here. I'll just tick through these. For biometric authentication when using video and audio, does it require them to be synced?
So Christian or Andy, one of you guys want to take that one, or I can?
Sure. In those cases, no. The face verification system that we deploy is independent of TSSV, so they don't necessarily need to be synchronized. You can have the audio buffer running at its own refresh rate, and then the visual system running at its own refresh rate. As long as you're able to multiplex the output signals based on those different system rates, it should work fine.
Thanks, Christian. How dependent is the solution on the quality of microphone and camera on a system?
That's another great question. In practice, our data tends to embody a fair amount of channel variance as it relates to speakers. And then likewise, our face system and has the same sort of properties. So there's a high degree of variation of each speaker within the data set. So it works quite well between channels. Frequently, you'll have cases where maybe you want to enroll with a particular microphone or on a cell phone and then have authentication run on a different device. We've designed around this use case and ensure that our system can work for these applications. Though obviously, when you have cases where the channel is the same for enrollment and verification, it tends to be more ideal and better. And we encourage customers to try to do that when possible. But in the worst case, we can adapt to those situations quite easily.
Okay. How well does the adaptation and also potential face recognition work with face masks, face shields, and so on in a medical environment when worn at times and not worn at other times?
Right. So for face mask, this is something that we have spent a little bit of time on, but at the current moment, I don't believe our face system is necessarily geared towards masked enrollments. Really, the best way to handle that currently is to produce 2 separate enrollments. A very familiar use if you have like a Samsung phone It'll frequently ask you if you like wear glasses or something like that to remove your glasses for the enrollment. I will say our face system is actually designed to get around that issue that is pretty prevalent in the industry. So glasses and variants in particular, our face system is quite good at, but face masks is something that we haven't spent as much time on.
And one thing that we could do is is you can combine, do a multimodal approach. So it could look at the face, and if it can't detect the face because of the mask, it could listen for a voice password, and we could definitely recognize through a mask. I did a demo or a little video some time ago where I think it was during COVID actually, where I enrolled without a face mask on, and then I was authenticating with a face mask on, and you could definitely hear the difference in my voice because the mask was covering it. But we were still able to authenticate that it was me speaking, even though I enrolled without the mask and then I was using the mask.
Thanks, Jeff. Okay, a couple more here. Why do text-dependent verification solutions typically have lower real-world FAIA rates than text-independent solutions?
Sure. So in practice, with text dependence, the linguistic variability is reduced significantly. So for text independent, it's really, any uttered phrase can result in a match, but with text dependent, it has to be the exact phrase that was enrolled. So in the case of adversaries trying to break into your phone, they not only need to know what your voice sounds like, but they need to know exactly what you said to create your enrollment. Frequently, this is something that's pretty prohibitive to do unless you have, spy cameras in your house that are watching you all the time. So really that helps to improve the security of those systems in practice.
Thanks, Christian.
Sure thing.
Why not use a neural network for the first stage instead of a statistical model?
This is another great question. So this is actually something that we are currently working on. At the moment, our statistical first stage was our legacy solution that was already quite accurate and works quite well. But neural solutions continue to get more efficient and better at small scale. So we're currently looking into replacing our statistical first stage or providing the option to use a neural first stage in place of it.
Okay. And you touched on this one a little bit, but maybe you could go a little deeper. When should I use text-dependent model versus a text-independent model?
Sure thing. So I think text-dependent solutions are really best for cases where you're really trying to do more person verification as opposed to person identification. So if you have, for instance, a cell phone that you're trying to gate access to or any sort of personal device, cases where it's really just one person interacting with the technology, I think text-dependent can work great for that. Likewise, if you have hot phrases, command and control, those types of applications, I'm thinking specifically of like autonomous vehicle markets where maybe you want to say, roll down my windows while you're driving the car and not have, your kid in the passenger seat or a family member be able to say the same thing. So those are a few examples of different cases where you'd want text independent versus text dependent.
Okay. Here's another one here. At what sort of SNR would you expect the voice authentication to begin to show poor performance in noisy environments? And are there specific noise types which you have qualified the solutions against?
Sure thing. Typically, we see degradation around the 5 to 0 dBA SNR range, all the way up to about 10 dB SNR. The system tends to perform quite well. The types of noises that we really optimize for are common noises that you'd see in the household or out in the world. So a few examples would be airport noise, malls. You could think of that as babble, sort of low SNR human speech fighting over the acoustic channel. And then autonomous noises as well. So in-car noise, those sorts of noises.
Thanks, Christian.
Okay.
What is the benefit of a multi-stage approach for TISV or TDSV as opposed to a single stage?
Sure. So what the multi-stage allows us to do is leverage or essentially come up with a solution that is not excessively compute intensive, but also has all of the nice properties of a more heavyweight solution. So the first stage is able to filter out a lot of the easy cases, and then we punt the much more difficult cases up to the more heavyweight neural solution for cases where the statistical model either fails or just doesn't perform as well. Particularly noise, I think, is where that comes into play a lot in practice.
Okay, so I don't see any more questions in the Q&A. I'll give folks just another minute to submit any questions to our panelists here. As we give folks a minute here, just a reminder. So after the webinar, we'll send the recording and the slides out to anybody who registered. So you can watch it again, forward along to your colleagues, that sort of thing. All right, so I don't see any other questions come in. If you do have other questions that come up, respond to the email and we'll connect you with somebody to help get those answered. All right, actually, let's end on one. I see one more come through here. You mentioned scene detection and noisy environments. Does this mean you already have a model that performs well in such conditions, or do you first apply denoising and scene detection and then run the model?
Andy, I think this might be a good one for you.
Yeah, I mean, the scene detection, I assume it's a sound scene tracking that I was talking about. So what we do is we in the solution is we do not denoise. What our models are usually trained with is noisy data, and when you have, for example, music as a prominent sound, you would have other noises in the background, and music would be your most prominent one. And then you can have multi-labels so that you can have more than one background sound at once, and you train those models accordingly. So this is how we currently usually handle it. We tend to avoid a specific denoising stage currently, but rather try to anticipate what noises might be happening in certain environments and actually model for those specifically for the solution. I hope
Great.
that answered that question.
Thank you, Andy. All right, so let's go ahead and wrap things up here. Jeff, Christian, Andy, thank you for your time and expertise today. Audience, thank you for all of the wonderful questions. I'll follow up here shortly with a recording for you all. Thank you.
Thanks all.
Thank you.
Bye-bye.